So my name is Bryce, Adelstein, Lelbach. I'm very glad to be here on my tour of Germany. I'm given like 6 talks over 5 days. This is talk number 3. So I was in Frankfurt yesterday at the GSI Particle Accelerator talk there, and then I was at LRZ, a supercomputing center in Munich today, and then I'm heading to Berlin next for a meetup there, and then a meeting C++. And then I'll be going to the C++ committee meeting. So a little bit about me. I've worked on programming languages and compilers for over a decade. I served as the chair of the standard C++ library evolution group, which designs and standardizes the C++ standard library. I am a principal architect at NVIDIA. We have these amazing holiday sweaters. I got one for the entire family, including the dog. And I drive our strategy for HPC and data science programming models, compilers, and libraries. Historically, I've worked in C++. Now I do a bunch of Python stuff. And today, I want to teach you about the C++ execution model. This model is what makes C++ portable today. It's no longer about how many bits are in a byte or whether ints are 2's complement. That's all sort of settled. It comes down to the execution model, the rules and laws of concurrency that are shared now across all platforms. So C++ defines a standard for multi-threaded execution that is broad enough that any platform can implement it, from the world's smallest DSPs to the CPUs in your phone, to server CPUs, and even to GPUs. So to go on this journey, we're going to actually read through part of the C++ standard itself slowly, and we'll discover some of the core concepts and rules of the execution model and see how they work in the real world. So let's get started. So at the heart of the C++ execution model is the C++ abstract machine. And the C++ abstract machine is a portable abstraction of your operating system, your kernel, and your hardware. So the abstract machine is the intermediary between your C++ program and the actual system that it is run on. And the abstract machine isn't an actual piece of software. It's just an idea. C++ doesn't have a virtual machine like languages like Java and C#. This is really, it's just a concept, just a notion, a model, philosophy. So the idea is that you write some portable code like this, and then you want to deploy it on a diverse range of concrete systems. And your code gets mapped onto this abstract machine by your implementations. And then your implementation maps it to whatever actual platform you're running on. So C++ programs describe operations that are performed on the abstract machine. C++ implementations define the characteristics of the abstract machine and then translate those operations on the abstract machine into operations on the system themselves. So the abstract machine's model is actually really, really simple. You've got a collection of threads that execute operations on objects that reside in flat global storage. That is it. That's all that C++ is. The entire complexity of the abstract machine is just here. Now, there are 2 key components here, threads and storage. So we'll start off with storage. Storage is flat in the abstract machine. There is no notion of hierarchy like caches, etc. There's no notion of NUMA, etc. It's just flat global storage. Objects reside in this storage at a single memory location. Every byte has a unique address, and no 2 bytes have the same address. Now, some objects may not have a unique memory location. For example, like eligible empty base classes or objects that get marked with no unique address. And an implementation is allowed to store two objects at the same machine address or not store an object at all. For example, let's say that you have an int and you never take the address of it and you never modify it and its value is a literal. Well, then the implementation doesn't need to store it because you can't observe that it's not actually stored. It sort of conceptually resides somewhere in memory, but you haven't done anything that would notice that. So the implementation can just not actually store it somewhere. Now, an object cannot have more than one memory location. If an object could have two addresses, we would no longer be able to compare object addresses to check for object equality. Consider the self-assignment check in this assignment operator. And so this is the sort of thing that would break if we had something like std memmap, because then you could potentially put the same object at two different addresses. So every thread in a program can potentially access every object and function in a program. So given that, let's look at a couple different system architectures and see whether they meet the constraints of an abstract machine. So here we've got some system. It's got processes that are running some virtual memory, virtualized over some main memory. We've got two processors. There's some caches, and the processors view into this main memory. This is a pretty typical CPU architecture. The answer is yes, this is fine. This is an implementation of the C++ abstract machine. But what if we have two processes running on this system? Can we say that these two processes together consist a C++ abstract machine, that they've got, each one has their own process local memory, and then maybe they have some shared memory that they can use to talk between themselves? This is not currently covered by the C++ abstract machine because the threads in process 0 can't access objects in process 1. And also, we could potentially have objects that are mapped in that shared memory and that would have two different addresses in the same program. So this one doesn't count. C++ doesn't cover anything like distributed memory or shared memory, IPC, etc. That's out of scope for the standard right now. Now, what if we have a system with two types of processors, each with its own distinct memory that is inaccessible to the other? For example, CPU and a GPU, both with private memory. Well, this also doesn't work. This violates the C++ storage model because we can't have objects that are not globally accessible. So, for example, a CPU-GPU system needs to have unified memory to support standard C++. So now, let's move on to talk about the primary type of actor in C++, threads of execution. So a thread of execution is a single flow of control in a program which evaluates a function call. And threads may run concurrently. So there's a main thread of execution in a program which evaluates the main function. And std thread and std j thread also create a thread of execution which evaluates the invocable object that is passed to them. Now let's talk about how initialization interacts with threads. So variables with static storage duration are initialized as a consequence of program initiation. Variables with thread storage duration are initialized as a consequence of thread execution. So they're created before the thread starts executing and they're destroyed afterwards. Okay, so threads evaluate a function call. What does that mean? What does it mean to evaluate a function call? To understand what evaluating a function call means, we first have to understand what evaluation means. And to understand evaluation, we first have to understand expressions because that's what evaluation operates on. So an expression is a sequence of operators and operands that specifies a computation. So for example, a function call, we talked about that one. Calling an operator, initializing an object. Now, sub-expressions are part of a larger expression. So for example, here we have a statement that declares and initializes a variable of type t, and this contains a number of sub-expressions. So there's a call to the constructor of t, an indirect function call, a dereference designating the function being called, and the expressions that produce the arguments to the function call. So full expressions are top-level expressions. They're defined as any expression that is not a sub-expression. So full expressions may include sub-expressions that are not lexically part of the expression, such as the end of a scope, or which would call destructors, or a function call which may have default parameters. Well, the evaluation of those default parameters is part of the evaluation of that function call, even though that default parameter appears in a very different place in the code. So such implicit calls are considered expressions for the purposes of the execution model. Now, evaluation of an expression includes value computations and the initiation of side effects, but not necessarily the completion of those side effects. So there's two things there. We have the value computations, and then we start the side effects. So side effects are things that change the environment. So that could include reading a volatile object or modifying any type of object, calling a library I/O function, or calling a function that does any of the above. So, for example, the side effect of the A equals A plus B here, or modifying an object. The side effects of cout of A times A, well, we're calling a library I/O function, cout. And the side effects of foo of A plus B, well, we don't know, because we don't know what the side effects of foo are, but whatever the side effects of foo would be, that would be the side effects of this call. So value computations are the other part. Value computations are pure, and they have no observable effect. The completion of the execution of an evaluation does not imply the completion of its side effects. So just because an assignment has completed does not mean that the modification of the object has necessarily completed yet, that the store may not have actually happened yet. It could have been reordered in the program, in the actual assembly, or it could have happened, but it's still moving through the memory system. Or like when we do a cout here, this is probably the most obvious example. When we complete evaluating this cout, that doesn't necessarily mean that the I/O has actually happened. We've all probably experienced this, and some of us have probably written stood flush or stood endl to ensure that the stream is actually flushed. Because by default, this is a side effect that sometimes takes a little while to actually hit your screen. So given any two evaluations, A and B, within the same thread of execution, if A is sequenced before B, then the execution of A shall precede the execution of B. This relationship, sequenced before, is one of the handful of key relationships that we're going to talk about today. So this sequence before relationship is asymmetric. If A is sequenced before B, that does not imply that B is sequenced before A. And it's also transitive. If A is sequenced before B and B is sequenced before C, then A is sequenced before C. So each full expression is sequenced before the next full expression in program order. It's like here, if I've got some full expression A and then some full expression B, A is going to be sequenced before B. This part of the standard basically says that within a thread, stuff happens, stuff is sequenced in the order that it appears. There's a couple caveats. We'll get there. If A and B are indeterminately sequenced, then either A is sequenced before B or B is sequenced before A, but it is unspecified which. But A and B are not interleaved. One of these two happens before the other. You just don't have a guarantee which. Now, if A and B are unsequenced, then A is not sequenced before B, and B is not sequenced before A, which suggests that they might be interleaved. So let's review and think about the practical implications of this. So if A is sequenced before B, then A executes before B. This is serial execution, which is what we typically think of. This is our sort of default mental model. If A and B are indeterminately sequenced, then one of them executes before the other, but we don't know which. So it's one of these two orderings. And so this is we can think of this as being what you'd get with simple thread parallel execution in a lot of cases, or with something that's going to have an implementation-defined order. And if A and B are unsequenced, then their execution may potentially overlap. They may be interleaved, so any one of these four possibilities could happen here. So this can occur when you have vector parallel execution, when things may be vectorized, when a single operation may be merged with other operations. So let's look at an example using the C++17 execution policies. So here we're using the stood execution seek policy, which guarantees that each iteration is sequenced before the next within the same thread. If we instead use the par execution policies, the iterations may be executed in parallel by multiple different threads. But if we use the stood execution on seek policy instead, then the iterations of the loop may be interleaved. It may be vectorized. So we may move all the loads together and all the stores together and all the FMAs together. And this is useful because it allows us to then vectorize those operations. But now we've also interleaved all of these iterations together. In this case, if we're just doing it with floats, this may not be observable. But if you had some of your own types, this could become more observable. So what about statements? When we're dealing with the C++ execution model, it's best to just think of statements as being compositions of expressions. So statement 0 here, whatever it would be, is going to be sequenced before statement 1, because we can just think of them as being full expressions. And the condition of an if statement is going to be sequenced before the body of that if statement. And the condition of a while loop is sequenced before each evaluation of the body. It's a little bit more complicated for a for loop, but you get the basic idea. It sort of occurs in the program order that you would imagine. So the value computations, but not the side effects of an operator, are sequenced before the value computations, but not the side effects of its operands. The operand expressions to the following operators are going to be sequenced from left to right. But for the assignment operators, the operands will be sequenced from right to left. So it'll be evaluated from the right side, you evaluate what you're going to assign to, and then to left. All right, so now that we understand a bit about expression evaluation, we can finally dive into what does it mean to evaluate a function itself? Because remember, we said earlier that all that a thread does is evaluate a function. So if we understand what it means to evaluate a function, then we will understand what threads do. So when calling a function, every evaluation within the function and every evaluation not within the function are indeterminately sequenced. The expression designating the function is sequenced before the argument expressions. So this kind of makes sense. You figure out what you're calling before you figure out what you're calling it with. Now, each argument expression is indeterminately sequenced with all other argument expressions. And every expression in the body of the function is sequenced after the expression designating the function and every argument expression of the function. So a lot of rules here. We'll work through an example. So here we've got a function b, which takes two parameters and has a body body e, sorry. And we've got a call to another function g, which takes three parameters, the expression a, an expression containing a call to b, and the expression f. And that call to b takes two parameters, the expressions c and d. So a and e here will be indeterminately sequenced, and f and e will be indeterminately sequenced. And then b will be sequenced before c and d. And c and d will be indeterminately sequenced. But c and d will be sequenced before e. We need to evaluate the arguments to a function before we evaluate anything in the body of a function. And likewise, a through f are all sequenced before the body of g. So together, these four rules describe the sequencing of our function calls, which ultimately describes the sequencing of our entire program, as we can think of our program as just being a collection of function call evaluations, and then the evaluation of the expressions inside of those functions. So now that we understand the basics of sequencing within a thread, we need to understand two more relationships to understand concurrency in C++, how different threads communicate with each other. And the first of those relationships is synchronizes with. So a library operation A may synchronize with other library operations B performed by other threads. This is an asymmetric relationship. If A synchronizes with B, that does not imply that B synchronizes with A. And this is a relationship about library operations. So you can only establish the synchronizes with relationship using something that's in the standard library. So what are the ways that we can achieve this? There's a variety of different concurrency primitives. I'll list just a couple. First, there's atomic acquire release. There's mutex lock and unlock. And there's thread create and join. Creating a thread creates a synchronization between the person creating the thread and then the body of the thread itself. And then also things like barrier, arrive, and wait. And also parallel algorithm launch, and then the wait for that execution. So synchronizes with is a runtime relationship. You only have it if the operation sees it. So imagine that we have two threads communicating data with an atomic flag. The first thread stores to the data and then does an atomic store release to the flag. If the load on the right sees a value of 1, then we have a synchronizes with relationship. So if we read the flag as being true, then we've established a synchronizes with relationship between these two threads. And so the second thread does a load acquire of the flag, and then it loads the data if the flag was set. If it's observed that, and if it knows that it has this synchronizes with relationship, and then it's safe to do that. So in that case, we would have the relationship. But if the load doesn't see the store of true, if it reads false there, then we don't have a synchronizes with relationship in either direction. You cannot synchronize from a load to a store, only from a store to a load. So we would only have a synchronizes with relationship from the store to the load, not in the reverse direction, and only if we actually observe the value being stored. Now, another example, mutex unlock operations will synchronize with all subsequent mutex lock operations, any that would happen later in the global ordering. So next, we have the most important ordering relationship, happens before. So if X happens before Y, then X is sequenced before Y, so within a thread there's that inter-thread ordering, or X synchronizes with Y, or for some evaluation Z, X happens before Z and Z happens before Y, so a transitive property. So happens before ordering describes arbitrary concatenations of sequences before, which is the ordering within the thread, and synchronizes with, which is the ordering between different threads. So all operations within a thread that are sequenced before a synchronizes with will be observable to the other threads participating in the synchronizes with. So let's revisit that example that we just looked at to understand this a little bit better. The left thread here stores non-atomically to data, and then it does an atomic store release to the flag. The store to data is sequenced before the atomic store to the flag. So the data store happens before the flag store. And likewise, the atomic flag load on the right is sequenced before and thus happens before the non-atomic data load. And so, if the flag load on the right sees the flag store of true, then it synchronizes with the flag store. And thus the flag store will happen before the flag load. And that then transitively means that the data store in the left thread happens before the flag store. And because that flag store happens before the flag load, and the flag load happens before the data load, we then transitively know that the data store happens before the data load. Even though they're non-atomic operations, we know that they are safe and correct because we've established this ordering relationship. Now, happens before doesn't mean that something actually temporally happened before. Now, if you were able to write a program that witnessed this, then your program has some form of undefined behavior. But it is important to understand this. So for example, consider the function foo here. It sets x to y plus 1, and then it sets y to 1. So the assignment to x is sequenced before the assignment to y. But that doesn't mean that temporally in your actual machine code that these things happen in a particular order. It's just about what you would observe. So if you look at the assembly for this code on some compilers, you'll see that the assignment to y may actually be interleaved with the assignment to x. So first we load y into a register, and then we store 1 to y, and then we add 1 to the value in the register, and then finally we store that value to x. This is fine because you're just dealing with ints here. You cannot observe this behavior without doing some weird UB or something. And so because the compiler knows that you can't observe this behavior, it's allowed to order it in this way, which is important for optimizations. So again, happens before doesn't mean happened before. a happens before relationship doesn't mean that X actually occurred in time before Y. It's all just about observable behavior, not the actual behavior. And again, a well-defined program is guaranteed to observe things in the happens before ordering, even if that's not actually what happens under the hood. And likewise, happening before doesn't mean that you have a happens before relationship. Just because X occurred before Y in time does not imply that X happens before Y. In one particular execution of your program, or even in most executions of your program, X may occur in time before Y, but that is no guarantee. Even if you look at it in the assembly, that's no guarantee. It may happen to work, but that doesn't mean that you actually have a happens before relationship. To have that, you have to follow the rules set out in the C++ standard, which means either you need to have it sequenced before within the thread, or you need to establish a synchronizes with relationship. Now, if you rely on ordering that is not guaranteed by happens before, then you have a data race. So what is a data race? A data race starts with conflicting operations. So two expression evaluations conflict if one of them modifies a memory location and the other one reads or modifies the same memory location. So a data race occurs when you have two conflicting operations performed by different threads, at least one of which is non-atomic, and neither happens before the other. And any such data race results in undefined behavior. Now note that there's the important caveat here that if both operations are atomic, then you're fine. There's no data race. For example, if you're doing two different relaxed atomics, you won't have a synchronizes with ordering, but that's okay because both of the axes are atomic. So consider this program here. We're communicating an int between two threads. The int is initialized to 0. The producer thread writes 42 to data, and then the consumer thread reads from data and prints it. So we have two threads performing conflicting operations. They're both operating on the same data, at least one of which is non-atomic, and there's no happens before relationship. And so we have a data race, and thus we have undefined behavior here. And so that means that this program could print 0, it could print 42, but also it could print any random integer value. It could print nothing at all. It could crash. It could print out blank space characters forever until it runs out of memory. Any of those things could occur. If we introduce a synchronization primitive, such as a semaphore, we can get a happens before relationship. So the release here in producer synchronizes with, and thus happens before, the acquire in consumer. And the store to data happens before the release, and the acquire happens before the load. So therefore, the store to data happens before the load of the data. And so this program will print 42. It's guaranteed. And we could also use an atomic flag and acquire release semantics to get the same happens before relationship. Now here we're using atomic's wait interface to block until we observe the producer's store. But if we use relaxed loads and stores for the flag, we won't get a happens before relationship between the store and the load. And we're using an atomic here for the bool, but not for the data. So now we're back to having a conflicting operation because we have one thread writing to something that's non-atomic and another thread reading from something that's non-atomic. So relaxed loads and stores are not synchronization operations. And so we'd be back to undefined behavior. Now, if we instead make the data object itself atomic, and we do a relaxed store and a relaxed load, we'll have a well-defined program. And that should be atomic int, not atomic bool. Now, we don't have any happens before relationships here between the threads. But all of the conflicting operations are atomic, so we do not have a data race here. But we don't necessarily know what this program will print. It will either print 0 or it will print 42. It is going to be unspecified which of those two. But this is better than the UB that we had before because it's not going to crash, it's not going to print some other value, it's not going to run out of memory, it's going to be one of these two orderings. So now let's move on to forward progress. To understand forward progress, we have to first understand what execution steps are. So the evaluations executed by threads are delineated by execution steps. An execution step is the termination of the thread, an access of a volatile object, the completion of a library I/O function call, a synchronization operation, or an atomic operation. And the completion of an atomic operation could include things like spurious failures. So a thread of execution makes progress when it performs an execution step or a lock-free execution. That's about atomics. We're not going to get into that today. That does not complete because other threads are making progress. Now, some atomic operations may fail spuriously due to interference from other threads, and implementations are encouraged but not required to prevent spurious failures from indefinitely delaying progress. So, for example, on load-locked store conditional architectures such as ARM, another thread may repeatedly steal the desired cache line for unrelated purposes in between the load-locked and the store conditional instruction. And on those architectures, weak compare and exchange operations may fail spuriously, just for no reason whatsoever. And even when the atomic's object value is equal to the expected value, it may fail to complete successfully. Now, forward progress basically just gives you a progress that something observable should eventually happen. That's what execution steps are all about. It's about observable things, completion of side effects, or touching volatile objects, etc. Implementations may assume that all threads will eventually perform an execution step. So this has the implication that infinite loops that have no observable effects are undefined behavior, and thus your compiler may choose to just delete those infinite loops. But only if they have no observable effects. So for example, if you have an infinite loop that's polling on a socket, that has some observable effects. It is making progress because it's calling a library I/O function. So next, we have blocking, which is waiting for a condition to be satisfied before continuing execution. So blocking library functions are considered to continuously execute execution steps while waiting for their condition to be satisfied. And thus, blocking should make progress. Now, finally, we can talk about the 3 forward progress guarantees that we have in the standard. And they are concurrent forward progress, parallel forward progress, and weekly parallel forward progress. So concurrent forward progress is the guarantee that the thread will make progress regardless of whether other threads are making progress. The thread is an independent and complete thing that can proceed on its own. It doesn't need any help. So examples of concurrent forward progress include threads that are being preemptively scheduled by an OS scheduling algorithm that is fair, like fair share or round robin, or an unbounded thread pool that will add new operating system threads to the pool as needed to make progress. Parallel forward progress is the guarantee that once the thread has executed its first execution step, the thread will make progress. So once it's running, you know it will complete. But before it's started running, you don't get any guarantees. So examples of parallel forward progress include tasking frameworks where tasks cannot be interrupted, such as a bounded thread pool, or threads on NVIDIA GPUs. Weekly parallel forward progress is just the progress guarantee that the thread is not guaranteed to make any progress at all. So it's essentially no progress guarantee at all. We just gave it a nice name. So examples of weakly parallel forward progress include non-preemptive OS thread scheduling, tasking frameworks such that support task suspension, such as like fibers or like a lightweight user mode tasking library where it's possible to suspend tasks. Now that's different from a lightweight user mode tasking library where you cannot suspend tasks. That would have parallel forward progress because once the thing starts running, you have a guarantee that it will complete. So what guarantees do we get from the main thread? This is completely implementation defined. And what guarantees do std threads make? Again, completely implementation defined. So on most popular platforms that have an operating system, this will be concurrent forward progress. On Mac OS, on Linux, on Windows, you're going to get forward progress from your std threads and your main threads. It's spelled out this way because on embedded platforms, or maybe platforms with no threads, you may have weaker guarantees. On platforms with no threads, std thread may be supported, but it may not be able to make that strong guarantee that it's going to always make forward progress because there's no actual hardware concurrency to do that. And because, at any point in time, some interrupt could come in and completely, mess with you. So finally, let's talk about boost blocking. So boost blocking is when you block on a thread with weaker forward progress guarantee. And when you do that, you want to preserve the calling thread's forward progress guarantee, because otherwise you would weaken it. So if a thread with concurrent forward progress is waiting upon a thread that has only weakly parallel forward progress, then that thread with concurrent forward progress may wait forever. And so what that thread wants to do is it wants to in some way ensure that it can donate its strong guarantees to whatever it's waiting on. So when a thread P boost blocks on a set of other threads, the forward progress guarantees of at least one of the threads in S is temporarily upgraded to P's forward progress guarantee. And this is repeated until the blocking condition is satisfied. So it's unspecified which thread or threads in the set S are chosen and for which number of execution steps. So boost blocking ensures that your children threads make progress, but not your siblings. Boost blocking does not protect you from inhibiting the forward progress of non-concurrent threads when using synchronization primitives. So let's work through an example. Here's a simple implementation of a thread pool with a fixed number of workers. We have a queue of callables and a mutex. And then execute async here enqueues a callable and returns a shared pointer to an atomic bool that will be set to true once the work item has been executed. This is just a poor man's future sender. And then we have a wait function that takes one of the tokens returned by execute async and waits for it to be ready. So each worker thread in this thread pool is going to execute process items, which contains this loop here, where it's just going to try to pop stuff out of the queue and then execute that stuff, and it'll just do that forever. So that loop just calls try-pop, and try-pop locks the mutex, and then it checks whether there is work in the queue, and if so, it pops that task from the queue, and then it executes it. And the tasks in this queue can be thought of as threads of execution with parallel forward progress, assuming that they're being backed by OS threads with concurrent forward progress. So the idea being that once you start executing one of these tasks, they will run to completion on the worker thread. Now, suppose that one of the tasks enqueued in this thread pool wants to parallelize its work. And so it spawns some children tasks to process part of the work in parallel. And then it performs part of the work itself. And then finally, it waits for the children to complete. But what happens if the thread pool has only one worker thread serving it? Well, then the worker will start executing the outer task here, which enqueues the children and then blocks pending their completion. But those children will never complete. There's no worker to execute them because that worker thread is blocking, waiting for them to finish. And so it's necessary for task join to boost block, to pull tasks from the work queue and to execute them until the blocking condition is satisfied. And to fix this, we need to modify wait to boost block here. So any thread that calls wait needs to ensure that the work it's waiting on will make forward progress. Now, to do that here, they have to make sure that the entire queue makes forward progress. And so instead of just unconditionally waiting on the token for our task, we can check the token in a loop while also processing work items ourselves. And this donates the calling thread, the blocking thread that's calling wait. It donates that thread's forward progress to the work that it is blocking upon. And this will ensure forward progress. So with this change, even if we have just one thread in the pool, this code will be fine. Because when we hit the waits here, instead of blocking forever, it will pull things out of the queue until it eventually gets to these children tasks. And then our program will successfully complete. So in summary, the C++ execution model on a single slide. We have threads that evaluate expressions that access and modify objects in a flat storage space. Evaluations within a thread is driven by the sequenced before relationship. Interactions between threads is driven by synchronizes with relationships. And happens before relationships just tie together sequenced before and synchronizes with relationships to describe ordering within and across threads. And forward progress gives us some promise of eventual termination. Now, I've made some simplifications here, and I've ignored some corner cases. So memory order consume makes all of this a lot harder to explain. Also, signal handlers. Don't really need to worry about either of those things that much. The basic ideas are sort of the key takeaway. And if you want to learn more about parallel programming and algorithm design, my buddy Connor and I have a podcast called ADSP. It's available on all streaming platforms. Go subscribe now. We do not have stickers yet. I know we've been promising for a year to have stickers, but we're working on it. All right. Thank you all for your time and your attention. And this is a blue-footed booby that we saw in the Galapagos. My girlfriend took this picture. I'm very proud of it. So,
any questions? You might use the mic, and he doesn't have to repeat the question.
ooh. Oh, no, apparently not. We can probably turn the lights on too at this point.
Bryce?
Oh. All right, on the audio setting, I press mic 1. The red button that says, there we go. Okay, I have all the power.
So we learned about the execution semantic for the execution state machine for the runtime part. But we have a C++ concepts.
Yeah.
And they behave slightly different. At least that is my observation. How that compares to what we have today?
So ConstExpr does operate a little bit different. First of all, you don't have concurrency within ConstExpr, so everything happens within a single thread. So it's all just going to be governed by sequenced before relationships. And in ConstExpr, you also can't have UB. So anything bad that happens will just be ill-formed. But in terms of constant evaluation, in terms of the execution model, there's, you can sort of think of ConstExpr evaluation as having its own little abstract machine, and it's an abstract machine with a single thread only, and that single thread has concurrent forward progress. It's an interesting question. Never thought about that one before. There has been some, people, I think we now have context for versions of the parallel algorithms, which again evaluate in a single thread, but every now and then people ask me, usually the context for people, like, oh, could we have parallel context for evaluation? I suppose it's a possibility that we could someday have this. I think it's a little scary, and it would be a little bit tricky to diagnose the UB, because to make that happen, you would have to be able to diagnose the race conditions. And if anybody has a deterministic way to diagnose race conditions in a program, then, give me a call. All right, other questions? We can all just go to bed. Yeah?
So when you were going through a sequence before, you were only showing wording in the standard where evaluations within a single thread are indeterminately sequenced.
Right.
So outside of weird things like calling parallel algorithms for vectorizing instructions, is there any way to get within the single thread instructions that are unsequenced?
I don't believe that there's any other way. Unsequenced was something that we introduced to give explicit blessing to vectorization. And it's important to understand that, as we talked about, when we talked about happens before doesn't mean happened before, the compiler under the as-if rule is allowed to do a lot of stuff if it can prove it's not observable. So the compiler is allowed to vectorize code if it can prove that it's safe to do so. The reason we have the unsequenced language and the reason that we have the unseq policy is because it's very hard for compilers to do that proof for loops, to actually prove that it's safe to vectorize a particular loop. And so we wanted to give some way for users to be able to say, hey, you don't need to run your proof checker on this loop and prove that it is loop invariant. Like, this is an assertion by the programmer, and then you, the compiler, are going to vectorize based on it. So if you're familiar with Pragma SIMD or Pragma OMP SIMD, that's basically the same thing that you can just stick on like a raw for loop, where it just tells the compiler, you can vectorize this one, trust me. I don't know that there's any other place, but the one place where it may be is some things relating to std SIMD. But I'm not sure about that because std SIMD is not a container type. It does not actually contain objects of type T, and so I don't know whether it needs to have those words there. I don't know, Gonzalo, do you know if there's anywhere else in the standard where there's unsequenced other than the parallel algorithms?
Maybe plus I plus I plus plus.
Yeah, it's maybe, yeah.
Maybe somewhere around there.
Yeah. But it's an interesting property of C++ that even when we talk about data races and concurrency, we don't actually allow explicitly for the possibility of things being interleaved between threads. It's only in this one place of the parallel algorithms where we bless this, taking your operations and just mixing them together like this. Any other questions? Yeah, we got one right there.
C++ is all about speed, right, for some people. And one of the fastest ways to communicate between two processes is with shared memory.
Yeah.
Do you think that we'll ever see shared memory considered in C++?
The problem is that every time somebody brings a proposal to the committee, what they bring is a proposal for std mmap, and you can't start there because we have to start with the memory model implications. If you could potentially have the same object mapped at two different addresses, that could potentially break compiler optimizations. There may be compiler optimizations that assume that every object is at the same address because the C++ standard says that today. And so, the C++ memory model today is something that is, enshrined in a bunch of different languages. There's formal proofs behind it. compilers optimize based upon it. Before we could look at standardizing something like Stoda mmap, we would need somebody to go and do the work and do the modeling of what extensions would we need to the memory model to allow for this possibility. And it's, it's not just the weird caveats of like having the same object at 2 different addresses. It's also the, what does it mean to have some external, agent that you're interacting with? There's a lot of different questions there. I think that, yeah, obviously we'll at some point have it. It's a big, feature request distributed. It's not just for inter-process communication within a single node, but also it's pretty important for distributed computing, for being able to do things like RDMA. But, I think more broadly, we would want to not just extend it to 2 different C++ processes talking to each other, but like it would be nice if we could have shared memory, and we could have semantics where that shared memory could be something that some NIC is writing to, and that NIC isn't running C++, it's doing things, and maybe that means that you have to do your accesses through volatile, but yeah, it's going to be important for us to do that work. Right now, nobody is looking into that. I think the committee would be quite receptive to it at this point. 3 to 6 years ago, we were focusing on walking before we were running. We needed to handle things like asynchrony first and figure that out, and just figure out make the core memory model, good enough for all the various devices we care about. We are now at a place where I think that that would be a natural next step. I think if people are interested in that, there's a number of memory model experts on the committee, and you could probably, reach out to people and get some input as to where you might be able to start. One of them's right here, Gonzalo. I'm not signing him up for work though, because he works with me. He's got way too many things to do. But I think that if you were interested, you could start a discussion on the committee, the concurrency mailing list with some of the folks there, and sort of see what we would need to do to get started.
We have a question from online. Last Michi, one of our viewers, wonders if you have any literature recommendations for people that want to learn more about C++ web programming.
I would say Anthony Williams has written a number of books that are quite good. I would watch any YouTube videos by Olivier Gros, who is the chair of the concurrency committee. I've given a couple other talks. I gave a talk called C++ 20 Synchronization Primitives, and my more recent Think Parallel talk, which I'm giving tomorrow at the Berlin C++ meetup, is also a good one to sort of instill some of those basic principles. Anthony Williams' books are probably, if you're looking for book literature, that's probably some of the better material out there. Yeah. Anyone?
More questions? Now's your chance.
Okay.
All right. Then, thank you very much, Bryce.
My pleasure.